Okay, dear friends, welcome back. This time we will continue from the idea of the reliability analysis or item analysis, where we had a set of items, and we are examining if they measure one uh, hidden variable or latent variable or something that makes all these items correlate. So we have something that we can't grasp, a concept that we are, or an abstract idea that we are interested in, and then we have questionnaires or uh, uh, tests on abilities or whatever, with which we measure this hidden thing here, and that uh, then we can use an item analysis to see if all the items work nicely together to measure this thing. Now, that's a situation which works very nicely if you have one hidden thing, one latent variable out here. But what about if you have more than one, say 1, 2, or 3, or many variables, which is actually often the case when we work with questionnaires, when we work with tests as well. Uh, we are interested not only in one-dimensional explanations about the world, but multivariate explanations. So that's where we are heading. We are trying to go from item analysis to factor analysis. All right. Behind all this stuff, we have, you remember from early on, the discussion about the correlations. So we have here the stuff we need. And the idea behind correlations is fairly old. So we are talking about late 1800s when the guys figured out how to do this that you see here. And the need for it was that they were interested in, for instance, in things like the inheritance of abilities. So they were interested in do the cognitive skills and rowing skill and whatever of the sons correlate with their fathers. So that was where they started out. And here you would have a typical situation with two variables, or well, at least two variables, and you would have the variance of the first variable here in this direction, second variable, and if they covariate, then you would have a typical situation here with high a positive correlation would be where you have a high in one end here. Typically you would have high on both or low on both. It could have a negative correlation where you would have being good in one thing would be the covariation would be such that you would be bad in the other one. Possible. Okay. And you remember the discussion about the different types of scales. Typically, we are interested here in interval scale variables so that we can actually use correlations, and that's the basis for the discussion today. And this was the first one. This is the second. So typically we would be in this situation. We have many correlating interval scale variables, and we are interested in how many dimensions, we call them factors in this case, how many factors, hidden latent variables, are needed to describe the covariance of this set of variables here. And as you see, we have already passed this one. Now we are getting here. So to typically the item analysis would be correct if we assume that there's only one factor, and the factor analysis would be specially built for the multivariate situation. Okay. As always, please feel free to find any good stuff on the net or any book or article, and if possible, please share it, because that's the only way we can teach each other and get to be more clever in this. All right. So, factor analysis. How many factors, dimensions do we need to explain the covariance, the thing that two or more variables correlate? And the question here is, do we have in our test or in our questionnaire, do we have many factors that are behind the way the correlations are, or are there just one or a few? And when we have technically found these factors, then we should try to identify them and even give them names. So naming is also part of factor analysis. We go from quantitative, seriously quantitative stuff to qualitative very quickly. There's no machine that can do that for you. The next question is the factor structure the same for different groups? We don't necessarily do this today, but the idea should be there in your mind. So if you're trying out a new questionnaire and you find a certain structure there, it would perhaps be worthwhile to see if the structure is stable, if you do it in, for instance, with the women and the men, or with the students with high abilities and with learning difficulties. If the structure is the same, that's already means that it works nicely in different populations. Or you could try it out in different languages and you could see if it works in the different languages measuring the same dimensions. We often have some kind of understanding, either from theory, reading previous research and thinking about the topic what our questionnaire is measuring. We have some kind of understanding of what it should be all about, probably from the person, if it's you or somebody else who has constructed the questionnaire. We know that we have put in items to measure certain things there. You can have many things or you can have just one thing. And then it is interesting to see if the structure, the correlations provided support for the structure that you have thought there would be. So you can test that, test it. The second thing here is that naturally, if we think of items on the same factor, they should have a relatively strong correlation. So that is something that we already spoke about with the reliability analysis. So we have convergent validity, which is the same thing as reliability, when the items measure the same thing. So they correlate strongly. And also the other way around. So if you have several factors, then according to the theory, some items that should measure one thing should correlate strongly there, and the other items that correlate strongly should measure the other item, but not so that these items go here, or some of them. So that would be an indicator that you are not actually, you have not managed to separate these two factors. But if you change the wording of your items, you may get them to focus better on the things that you are trying to measure. So that would be discriminant validity. We can also, if we are trying to construct a good questionnaire or test, we can also see if there is a correlation between the factors we get and some other known factor indicators that according to theory or common understanding they should correlate with, or either correlate strongly or not correlate with. So for instance, you could have constructed a mathematics test, and you would compare it with the grades of the students to see if it measures more or less the same thing. So those students who typically get good grades in math would also perhaps get good results in your math test. Or you could do it the other way around and see if it separates those who have typically been diagnosed with learning difficulties of some kind, especially some learning difficulty that has something to do with math. Okay, this last part is excellent if you do it, but it's not very common to see it done. But especially if you look for psychological articles on developing tests and questionnaires, they tend to do this well. All right, so the goal here is to find the optimal number of factors explaining the observed covariance correlations between a set of items. The optimal number of factors means that not too many, because that complicates the world too much. You have to talk too much. You have to write a long report if you have very many factors, but not too few either. So there's a Goldilocks in between there somewhere. And we're trying to find that Goldilocks number of factors. So we are looking for the essential characteristics of the observed world, but such characteristics that you can't measure directly. Otherwise, we would go and measure them directly. And in education, we very often have something, we very often work with things that can't be directly observed. So even if we look at observed somebody directly solving a puzzle or so on, and we can count how long time it takes to solve this puzzle or something like this, that time still for us is an indicator of the ability or skill or knowledge that person has. Okay. We are also interested in examining the structure of the phenomenon we are interested in, and concentrating the information on the items in as few dimensions as possible without losing something important. And we have, again, here it's typical that we have several names for things that are dear to us. So factors, dimensions, latent or hidden variables, all named for the same thing. But here we're talking about factor analysis, and with factor we mean the things that we are trying to get at by looking more concretely at the covariance of the items in our data. So There are different approaches to factor analysis. The traditional way is to do an explorative factor analysis, which is nice in situation where you examine topics, tests, questionnaires, where you have constructed a new one, for instance. So there's little prior knowledge or research-based understanding of how many dimensions there should be to explain this thing. More confirmatory factor analysis tests how well the data supports a theoretical model that we have. So you would postulate that there will be so and so many factors in this, and then you could also postulate which items belong to which factor, and you can test this. We won't go into that in this course. Unfortunately, there won't be time for it, but it's nice. We will have, however, approach almost halfway to this, so don't be too worried. The note here is important. In all psychometric testing, statistics, we should not first explore and then develop a model and then test this model with the same data, because of course then you fool yourself and especially the reader. If you have already developed the test so that it matches nicely the data, and then you test if it matches the data, you get the test that you get a factor structure that can be well adapted to this one set of data, but not generalizable. So the idea is that you choose from the beginning, do you do a traditional explorative factor analysis, which is mostly done, or do you do a confirmatory factor analysis if the thing you are studying is well known? That could be a good idea. Well researched and well-known questionnaire, for instance, that you could easily do this, but not both in the same study. All right, here we have kind of a picture of an exploratory factor analysis. What I haven't drawn here is that all these items in your data, all these correlate. The idea here is that you then have these latent variables or factors that explain the correlation between these items. So these influence the items. And because this thing lies behind both this and behind this, then that's the explanation why they correlate. And to be very statistically advanced, then you also have error factors. So you don't explain all the variance of the items with the factors. Something is lacking. You don't have 100% explanation ever. I think I haven't ever found one. Okay, so you look at one or more factors explaining the correlation between these items, and then you have different types of factor analysis, exploratory or confirmatory, but different types of factor analysis. So you would have here a typical orthogonal explanation. So here we don't have any correlations between the factors. They would be orthogonal, means 90 degrees. They would have nothing to do with each other. So this is a very clinical approach. We seldom have in education or psychology or similar human sciences a situation where we would actually have the case that we would not assume that the factors correlate. I mean, very few things in the world that human beings think or do are totally uncorrelated. However, this is where factor analysis started out. So when they invented factor analysis first, they couldn't do the correlation between factors. So they did what they could. So you have this orthogonal solution, usually not a good idea to choose it for obvious reasons. Human beings do things that are correlated. So this would be correlations between the factors, and that kind of a model is called oblique. So you would have nothing to do, factors that have nothing to do with each other, or factors solutions where there's an oblique angle between them, so they are correlated. When is it appropriate to use a factor analysis? Well, there are some restrictions. We should, first of all, have enough cases, research subjects. So the proportion of items to research subjects, if you think of how many subjects should you have items to research subjects. Yeah, how many research subjects should you have if you have a set of, say, 100 items? Then something like 1 to 5 would be already tolerable, and more than 1 to 5 is better. So 1 to 10 would be really nice. So let's start out with a 100 item questionnaire. Then you would actually need to have at least 500, but would be nice to have even 1,000 research subjects or cases. Nice, but not absolutely necessary. You can get by with lower numbers as well. But somebody might complain. Your opponent might complain in your doctoral thesis. Okay. That just means that the solution you get is perhaps not as stable and not as generalizable as one would hope. Also, there's a ratio of items per factor. So if you assume that you have a one factor model behind the covariance of the items, then you would do well to have at least 3 items. So 1 to 3 would be nice. You can add more and you can have a lot of items, but you shouldn't have less than 3. Actually, if you have 1 to 3, you start out with 3 items per factor, then you can't throw out any bad items. So yeah, you get easily into trouble if you have too few items in your per factor in your test or questionnaire. Also, the items measuring the factors should correlate enough. So if they don't correlate at all, then there won't be any good factor solutions either. And there are 2 measures that factor analysis programs typically report. One is a so-called Kaiser-Meyer-Olkin, or KMO, measure for sampling adequacy. We'll get back to that later on, but it should be more than 0.6. And you have the Bartlett's chi-square test of, I don't know how to pronounce that, sphericity. It should also be statistically significant. So the p-value should be less than 0.05, so less than 5% risk if you draw the conclusion that they do not correlate enough. And less than 5% risk that they do not correlate enough. Yeah, okay. They do correlate, in other words. Yeah, good. And luckily for us, in almost every case, these two go hand in hand, so that the KMO measure gives the same result as the Bartlett. Okay, quick look at how this way of thinking was developed. We started out with correlations, so we had Francis Galton interested in, among a lot of things, but among other things, the inheritance of intelligence. And he formulated the idea that there should be some measure of the connection between the fathers or parents' abilities and the children's abilities. And Auguste Brevet continued this project. Carl Persson was the one who continued and explained that this is the way it could be done, and the finalizing was done by Auguste Brevet. So that's what the machine first counts out, and then it produces a factor analysis. And the starting point was something of the similar kind as an item analysis. So they had a one-factor model with Charles Spearman, continuing the study on general intelligence. And then Louis Thurston and others went in for a more multifaceted explanation of the way cognitive abilities go together. So you would have something like word fluency, verbal comprehension, spatial visualization, number facility, and so on and so on. So a multi-factor model. Then they had to produce a way of doing the correct or getting at these with a factor analysis had to be multi-factor. And then they applied the factor analysis model into personality theory. So you have people like Allport, Raymond Cattell, Donald Fiske, and so on and so on. And this goes on. So you in testing, in student selection into universities or schools, all kinds of situations. Still, we first try to improve our instruments, tests, or questionnaires, make them as short and comprehensive as possible, and then when they work nicely, we can use them to find suitable candidates for employment, or suitable candidates for education, or we can help them if they are having trouble, and so on. And you might notice here that we have already spoken previously of Pearson's correlation, Spearman's correlation for ordinal scale variables, and we even had Cattell's scree test. We will have soon Cattell's scree test. And life has changed rapidly. So we also have Henry Kaiser, who kind of was one of the guys who pioneered the use of computers for factor analysis. So luckily, we don't have to do this by hand as the pioneers did, because it was a terrible job. but nowadays you can do it really simply, and it doesn't take hours or days or years of your life. Okay. In the exploratory factor analysis, factors are defined mathematically, so to say, based on the correlations. We assume, this is just putting the parts together here, we assume that the factors are influencing the items we have in our test or questionnaire, and we can decide how many we don't have to have a previous understanding or conception about the number of factors. We can decide it during the process, and after we have factor analyzed, we can then identify and name the factors we have come across. That's the main part here. So what do we do? First of all, we assess how many factors we should have. Then we do the actual factoring. Then we rotate, which means finding the most elegant and understandable solution. And then we go on with producing factors. Okay, so the first question is how many factors? And there are different ways of approaching this. One is, as I already mentioned, the screen test by Raymond Kattel, and also Kaiser had an own criteria. We'll get into both of these presently. So how do we do this? You start out by analyze dimension reduction. So we are close to the reliability analysis we found here. Dimension reduction, factors, and then you go on to select the items you are interested in, just as before. So some things don't change, and that's nice. Then that's expertise. You can select the variables you are interested in, and then we have the first box of factor analysis comes up, and it has pre-selected principal components, which is actually not factor analysis, but it's useful for this finding the correct number of factors. So we use it here. You don't have to change it, and I would suggest that you select this unrotated factor solution. So that would be the main components, and then the scree plot there. I have also changed the down here. So based on eigenvalues greater than 0.5, it usually has 1 there, but this gives you a little bit more information. So we select that. Lowest down you have the maximum iterations for convergence. Iterations is just the machine counts again, or the program counts again and again until it reaches a better and better solution. And if you have too low a number, then it stops in between and complains, and you can add to this. So that's what was really important in early days, because then it could take days if you put a big number of iterations there. Nowadays it doesn't matter. Anyway, now I have selected those variables that you saw. I have put them into a correlation, made a correlation matrix. You can see the diagonal where they correlate 100% with themselves. And then you can see also the green area where there's a strong correlation, and this is the parental support. So you see in the correlations exactly the same thing as you saw with item analysis. Only here you now see the next item, the next factor already beginning, but it's too big to fit into the same picture. Then, as I said, you get two criteria for how suitable the correlation matrix is for factor analyzing. And the Kaiser KMO was supposed to be larger than 0.6, and now it's 0.844, so fine. And it was supposed to be significant. The Bartlett's test was supposed to be significant, and we have a value of 0.000, so that's also excellent starting point. Everything is go. There you go. Next, we have a table presenting our the variance explained by the factors, telling us how many factors we actually need. And here I would start out looking at how many components we have here. So an easy way would be to say larger an eigenvalue here is how much of the variance is explained by each component. An eigenvalue larger than 1 would indicate that there's more variance explained by the factor or component than a single item has. So a single item that doesn't correlate with any of the other items, that single item would have an eigenvalue of exactly 1. Okay, so we are very close here. And then here you can already see the same thing, but now in percentages, how large percentage is of the variance these components explain. And the last one is cumulative. So it tells us that the first 3 explain more than 60% of the variance. That's perfectly fine. It also shows us that you don't actually get very much more with a 4th component, and certainly not much more added value by adding a 5th, 6th, and so on component. So that already gives us a pretty good picture of what we can achieve by increasing and making the explanation more complex, increasing the number of factors. Something between 3 and 4 would be optimal here. Then, as we selected the scree plot, it produces this picture, and you have the variance explained by factors. And you can see this is the same thing as you had here, the eigenvalues, and you can see that the 3 first ones explain the majority of the variance. Then you have 1 borderline case, and then almost flat line down there. However, as I said, Cattell, it was the guy who invented the scree test, and I'm a stickler for what he said. So he has actually written an article in the 60s, if I remember correctly, explaining how this should be done when he invented the scree plot. And the scree, of course, is the junk, the rubble that is left if you have a mountain like the Alps or the Kilimanjaro or something, and it's broken down by erosion. Then there's a scree underneath it with smaller and bigger rocks and rubble and stuff. And the scree is relatively stable in its angle like this, and above that line, you can see the real mountain and real mountain tops. So here we would have 5 real mountain tops. In this case, we would have only 4 or 3 mountain tops sticking out above the scree. So looks like something like this. First of all, Kettel said that these should be drawn in proportion so that you have a figure where one step of on the eigenvalue scale is proportional. The dimensions are such that one step on the eigenvalue would be 10 steps on the number of components. So you just have to squeeze the picture, the first picture you get. Mostly you have to squeeze it. Then we can draw already, if we have this proportion, then we can draw a scree line here. And as you see, there's an angle just as there is under the mountaintops. It's not flat like this, except if you don't have any random noise in the measurements, but we always do, so it's always a little bit, it's never as flat as this, it's slightly or more angled. And then we have here already a clear indication that we have one component where there's probably just one item on it, or maybe there are 2 components, 2 items, but they have a very low loading on it. They are not very strongly on that third component, fourth component. But there is something between 3 and 4 here, would be the scree test result. And Kaiser, as I said, he also was important in its development. So he said that if we have something above 1, then that is where we should focus on our number of factors. So combining the scree and Kaiser's criterion would say, scree would say 3 to 4, probably 3, and Kaiser would say 3. But only just, so because this was very, very, very little under the line of 1. Okay. Then we tick the box with the unrotated solution, and here you can see already that there's something going on. So you have those items indicate that we have a first component, a second component, and something of a third component, and then a little bit noise. But very little stuff going on as for a fourth, fifth, and sixth, and so on component. So the explanation we get here is simple and can be simplified. Now we have decided, let's say, on 3 factors. We go back to the extraction. We do the thing again. We don't have to select new variables because we are doing it on the same. But here we would now we can unclick the annotated solution, the scree plot, and so on. But what we would do, however, is choose maximum likelihood as a method, and we would also here select 3 variables. Sorry, 3-factor solution. Then we would go to rotation. So up here, rotation, and select. There are different. Varimax would be a typical orthogonal solution, and oblimin would be direct oblimin would be a nice and oblique solution. So we would select that. Going ahead, what else can we do? What we can go to the options up here, and select exclude cases pairwise. I'll briefly explain what's going on here. We have a situation where not everybody answers every item. Some don't turn page and don't answer the last questions by mistake. Somebody just wants to end the session early. Either way, they have answered something, and we would use that as well as possible. Then my suggestion is that you select either exclude cases pairwise or replace with mean, simply because if you do this, what the program suggests, exclude cases listwise, then each and every guy that has left even one item unticked would be out of the whole analysis. So we lose a lot of data with no good reason. The reason I say you can do either of the following is if you exclude pairwise, then you have all the information of this first variable with the second with the third, the first with the third, and so on. So every combination uses all the data we have to count the correlation. And similarly, if you replace with mean, that means that is, if you look at the formula for the correlation, you realize that it has in it the distance from the mean, which means that those individual scores that are far from the group mean, they have a lot of influence on the correlation, as we were talking, and those that are precisely on the mean, spot on the mean, those don't have any influence at all. So you can this replacing a missing value with the mean doesn't change the correlation at all. So those individuals are also included without any strange findings. So the two last are actually much the same for all practical purposes. All right, then we come up with this. I just made it bigger so that you could see it. The communalities tell us how much these three factors explain of the variance of the item, each and every item. So this is very close to an item analysis, reliability already. And what you can see here is that most of these have a high communality, not so high. Some of them are lower, and one of them is really low. So here, if this was the result of an item analysis, we could easily say that, okay, at least the last item should be dropped, but maybe these two as well. And of course, the same thinking goes for factor analysis. Here we could, however, also increase the number of items, factors, to see if actually, for instance, the last item would then load on a factor of its own, but still it would be a pretty weak show. Next, we get the so-called goodness of fit test. So I said that we are close here we are exploratory because we didn't figure out the number of factors to start with, but we are also on the verge of confirmatory. So when you select the maximum likelihood model that we started out with, it gives us this goodness of fit test. So it again has a chi-square, degrees of freedom, and here we have the important information that our model is the number of factors is not quite sufficient to explain all the variance in the data. So this is not actually very good. And of course, there's a good reason why it's not so good. If we look at the commonalities, if we drop the bad items, and especially this one, we would directly already have a better fit, quite a lot probably. If you want to have, if you have a lot of cases, and here we have a lot of cases, more than 30,000, then typically this is always significant. So you never get kind of never get a good result. No, there's always some variation and distance from between the factor model and the realities. However, if you select just a small sample of your big sample here, then we could find a model, factor model, even a 3-factor model that would fit nicely to this data. That's number one. Number two, if you look at the proportion between the chi-square and the degrees of freedom, it's now something like more than 10 times. So 7,000 is more than 10 times 63. But, sorry, 10 times. More than 100 times 63. But if you find a chi-square that is something like 2.5 times the degrees of freedom, then it begins to be close enough. You get there by dropping the bad items, and also sometimes trying your model on a sample of the data, a smaller sample. So this is, it picks up the signal, very, very small signals of deviation from the model, and that's why it gives the significant result here. Next, we find the pattern matrix, and we can see that our solution, even if it's not perfect according to the goodness of fit, it's still really, really good. So we have a nice structure here with a parental support, the thing that we did on item analysis. Sorry, I'll get lost here. And then we have the next set here is something to do with anxiety at school. And the last one has to do with performance orientation or motivation. And the last item is something else completely, so that's why it doesn't fit into the picture. And as we chose an oblique rotation, we have one further table, and it shows us the correlation between the factors, which are actually surprisingly low. That's because they really measure totally different things. My concepts about my parents, my concepts about myself, and so on. Just as we did with the item analysis, we can also use the results of the factor analysis to produce new variables which would compress and then express that thing that the items in a certain factor express. And one way of doing it is to select here from the scores the saving the factors as new variables. If you click it, then you will find at the end of your data set new variables, as many as you have factors. So here we would have 3 new factors, and they would be then also z-scored, so standardized, so that their average would, the mean would be 0 and the standard deviation 1. And dear folks, that's about it for today. Thank you very much.